an algorithm for partial differential equations. But I'll introduce everything first. Okay, there was a delay, so I'm sorry about starting late, but this talk won't be too long, so it's fast enough. Yeah, so the general title would be, could there be a quantum algorithm for nonlinear differential equations? Solving nonlinear differential equations classically is hard. There are a few analytical solutions, and it suffers from this curse of dimensionality. So as you discretize space and time, the exponent for the dimensionality, well, obviously that increases, and it's in the exponent, which is this so-called curse. Could quantum computers help? Well, in theory, potentially. The Hilbert space grows exponentially, and the dimension would then become a coefficient. And we know that there's an exponential speedup with some caveats for linear systems. So the question is there a speedup for nonlinear partial differential equations? And spoiler, not in general. This is the Lorentz attractor, which is just quite a nice, simple system, and it's chaotic, and that's a chaotic regime. So I'll address whether you could do this with an exponential speedup at the end. So a general nonlinear differential equation, a simple one, which is also considered in this paper, which introduced this algorithm for distributive nonlinear differential equations, is the Berger's equation. It's a really simplified one-dimensional model for fluid mechanics, but it contains all the essential components of PDEs in general. You have some time evolution. You have a nonlinearity where you see the U twice. You have a diffusion term, and then some forcing function, which can be, in general, quite complicated. And then we can say, okay, just looking at this, what could a quantum computer do? Well, we know we can solve linear equations with an exponential speedup. And linear is a good place to start with quantum mechanics because quantum mechanics is linear. So the first step in their algorithm was turning this nonlinear PDE into a linear system. And then we solved the linear system with the well-known HHL algorithm and then subsequent improvements. So this is saying the real problem here is bounding the error on turning a nonlinear differential equation into a linear system. So how do we do that? So yeah, we start with this Berger's equation, and the first step is discretization. This is discretization of space. So U would be a continuous function of x, rather than continuous. Now we make it discrete with spaces between the U. So UI is a point on a grid, and the space between them is delta x. And then the derivatives become differences divided by the grid size. We then linearize this system. This is Kalman linearization is used in reference 1, and I'll talk about Kalman linearization in detail in a bit because this is where the error really comes from. But after Kalman linearization, we end up with this dy by dt, some matrix y plus some bt, which contains the forcing term. And then we need to evolve the solution in time. We want a solution over some period of time. And we take time steps, delta t, and we use this Euler-Ford method, and there are other methods. Well, they use this Euler-Ford method. There are actually other methods, and the Euler-Ford method is more of a proof of concept idea because typically it's considered unstable. So yeah, we just take each time step, and then you apply only a small small time to the initial state. And you keep doing this, but what you build up is a big matrix to do all of the time steps in one go. So you solve all the time steps simultaneously, and that's how you have a linear system of equations to solve. So I'm going to talk about Kalman linearization in particular because this is a big source of potential error in this technique, turning nonlinear differential equation into a linear system. So, limitations, Kalman linearization. So we're taking this finite dimensional nonlinear system and we can turn it into an infinite dimensional linear system. How do we do that? So nonlinear terms are elevated to variables, so that u squared term will become its own variable. And then we track those changes over time. So just by chain rule or product rule, we have this u du by dt. And then we do the same for cubic terms. And then we have this infinite vector of all these new variables. So we have all our u variables, our u squared, u cubed, up to infinite. And infinite is required for precision to exactly map the equation. Yeah.
Sorry, how do you understand the first equation? Because like you have only u, then you have like u squared on the other side.
Oh, sorry. What was that?
Like I don't understand the equality in the first equation.
This.
Yeah, because you have like u tensor u.
Yeah.
But on the other side you have only u. So
yeah, but f2 doesn't have to be square. So f2 in this case isn't square. And then
what is f2 then?
it would be n times n squared if n is the size of u. Because then, so like if you have a fat matrix, then you can have a long one. So u tensor u is like much longer than u.
Sorry.
Yeah.
So that will be equivalent to write u f2 squared and then u. I mean, you can get a square matrix if you express the quadratic term as.
Right. Yeah.
It's kind of a linearization.
Yeah, that should be possible. I don't know if the f2 would be full size then. No. Yeah. Let me think about that.
Okay.
Is that do you know if that's possible?
I don't know. I was wondering that when I read the paper. Yeah. So, and what's the equivalence of the eigenvalues of that matrix and the properties that you want to know of f2 compared with the square form of f2? That will be equivalent in terms of.
Because in general, this f2 is quite large.
Yeah.
But if you make it a square, I'm not sure. It feels like you might lose something.
Yeah. I don't know.
But
yeah.
Interesting. Oh yeah, shall I repeat the question? So the idea is, Javier said whether you can have this f2 in the middle and a u on each side, rather than writing it in this way. And I'm not sure. Okay, so then you end up with this linear equation of time evolution, but this y is infinite dimensional. That's the problem. So, of course, we have to truncate at some n. We can't solve an infinite dimensional equation, and this is where the error is introduced. So at some n, we stop, and this y is still, in general, very long. With up to u tensor n times. It's a really big vector. But we can bound the error for arbitrary time. So if the eigenvalues of f1, which is this linear term, if these are all negative, you can define this Reynolds-like number. And I say Reynolds-like number because we have a spectral norm of f2, Okay, f2 isn't square, so this is the largest singular value in the single value decomposition. We have so we have a ratio of the size of the nonlinear term with the a norm for the size of the linear term. So this is why it's somewhat like a Reynolds term. And then of course we have this initial state, the size of the initial state, and then we have the size of this forcing term. So the forcing can't be too large compared to the initial as well. And the proof is that the Liu et al. Paper showed that if R is less than 1, with some other limitations, that the error on Kalman linearization is always bounded. So for arbitrary times. But this is quite a major restriction. This is distributive solutions only. So this is just to summarize. The eigenvalues of F1 are all negative. We have this Reynolds-like number which has to be less than 1. But there are two more. That the solution decays for all time. I mean, in another way, this could be thought as distributive. But actually, this was slightly relaxed in a subsequent paper, just that it doesn't actually have to monotonically decay. There can be some oscillation. And then another restriction, the solution cannot decay exponentially to 0 because the amplitude of this good space will appears in the time complexity like un over ut. So if ut decays exponentially to 0, that blows up the complexity. Okay, so there are a lot of limitations. But what about for r greater than or equal to 1? So the proof before was that for r less than 1 it definitely works. It doesn't say that for r greater than 1 it definitely doesn't work. In the Liu et al. Paper, they found an r greater than or equal to √2 where there cannot be an exponential speedup. And the method is the state discrimination task. So imagine you have this black box and it prepares either state psi or phi. And they have very large overlap, so it's hard to distinguish which one you have. Then the minimum number of queries required to distinguish them is goes like 1 over the separation, 1 over the epsilon. So what we do is we construct a PDE whereby if you could simulate that PDE, then the number of queries required to distinguish an initial state of psi and an initial state of phi would grow like logarithm or polylog 1 over epsilon. This is not possible. It would be faster than the minimum time. And so you can say that this PDE could never be simulated efficiently, exponentially faster than classical on a quantum computer by any quantum algorithm, not just the quantum algorithm in this paper. And so they use this technique for 1 over √2, but we proved for r greater than or equal to 1, there is an algorithm. Their algorithm is, there is a PDE where their algorithm, or any algorithm, cannot work, which means that the algorithm of Liu and Charles is worst case type. So in the worst case, this is as good as algorithm as you can get. But there are r's greater than 1 which can be solved efficiently. So for example, the Burger's equation, you can solve like r around 44 and you'll still get a solution. So it's an interesting point about saying, is there a limitation for all PDEs? So could we find a class of PDEs where you could never have an exponential advantage? And we introduced this Lyapunov, or this Lyapunov exponent is a well-known measure of chaos from classical mechanics and or dynamical systems. And it's defined, I mean, more intuitively as an exponential separation of trajectories which start very close to each other. And we proved that exponential advantage is not possible for positive Lyapunov exponents for solutions that grow so exponentially. So let me just demonstrate. We constructed this system where all the eigenvalues of the linear term f1 are negative, but it actually has chaos, which is actually quite hard to find a system like this. So if we start with initial condition far from this fixed point, we have this chaotic solution, and it sort of has a similar kind of behavior to this Lorentz system. And then we can have an initial condition close to a fixed point where we move just a little bit along a real eigenvector, and the solution will decay to the fixed point. So the question is, can this be solved exponentially? Can it be an exponential quantum advantage? And the answer is no. That has a positive Lyapunov exponent. So you can measure trajectories starting from the initial point, just deviated a little bit, and then track those changes. And then these are orders of magnitudes different. So you can't see that. But this is like 10 to the minus 8, this is like 10 to the minus 2. And then the this line, the gradient gives you the Lyapunov exponent, which is about 0.1. So positive. And so we proved that this cannot have an exponential quantum advantage no matter what algorithm you try. But what about this one? I mean, it looks quite simple. It's actually, it's not proven that you can get an exponential quantum advantage because the R is really big, like 40,000, which is quite interesting because the solution looks so tame. And just out of interest, the solution for this is 100,000, so the R value, the Reynolds light number. But what we can do is we can look at how the error, so you can't see this, this is really small error, like 10 to the minus 10, for the Kalman linearization with different truncation orders. But what we see is that they're all decaying exponentially. So it's bounded error for arbitrary time. As time goes up, the error is well bounded. Whereas, to compare, this is a constant error already. So these times are the same. And after a very short time, you already have a very large error if you try and Kalman linearize this system. So, to summarize, only a small class of PDEs can currently be efficiently solved. They have to have dissociative solutions, low nonlinearity, and for sure a negative Lyapunov exponent. So why most nonlinear PDEs cannot be efficiently solved is that your linearization breaks down. So you have this unbounded error as time evolves. And the reason, is kind of intuitively that quantum mechanics is linear. So nonlinear problems are out of its scope in a way. And it would allow too fast state discrimination. This is the proof tool. So some open questions would be, which fluid equations and regimes lend themselves to advantage? So not all fluid systems or nonlinear systems are turbulent or chaotic. Are there stronger bounds on regimes which are possible? For example, we really wanted to be able to say that if the Lyapunov exponent is negative, you can have a exponential quantum advantage to show that the algorithm would work. Actually, this is not the case. For negative Lyapunov exponent, we can construct systems quite straightforwardly, which it looks like the Kalman linearization would blow up. So then you could ask if there's other linearization techniques which would be amenable. And so then we could say, what about simulating these nonlinear PDEs for just short times? And say, okay, maybe you only want a little bit of dynamics. Is there something useful or for an advantage there? And then we can ask, okay, forget exponential advantage then, what about polynomial advantages? That could still be useful or interesting.
So negative Lyapunov exponent is a necessary condition, but not sufficient, right?
Yeah, not sufficient. Okay.
So I understand what some part maybe I missed or something like this, right? But if I understand correctly, if you so the reasons why some equations are not exponential advantage, it's very similar to the reasons why one can prove very classically that you don't have efficient or polynomial, let's say, algorithms, numerical algorithms to solve these kind of equations, mainly because they just spread too fast and they are too. So in order to keep the error bounded, you need to grow exponentially the number of time steps in this repetition time, right? And this is purely classical. But do you have another example? Any of the examples that you have is able, you are able to prove that you can solve it, you cannot solve it classically efficiently, but you can do it quantum mechanically. Because what I saw in general, and maybe I missed something as I said, but is that you have found algorithms that solve quantum mechanically efficiently, but I don't know the classical counterpart.
Right, but you can say that the classical algorithm for solving, say, like Berger's equation, would involve the linear systems solver at the end, and that's where you have the exponential speedup. So it's just saying that as soon as I've mapped to this linear system equation, then I have my exponential speedup. So it's only coming at the end.
But for instance, classically, there are also situations in which you have a linear system, you have a sparse matrices and something like that you can speed up. Also classically, the algorithm.
Right. Yeah.
So I don't know. I mean, I don't know what I mean is if you have any proof that one of the examples, or whatever the example you have taken, cannot be efficiently or cannot be speed up.
Yeah. No, so I don't have a specific nonlinear PD example, but my answer would be that basically constructing a PDE which gives a linear system which has a advantage is the same question. So basically, in the HHL algorithm, if there's a speed up there, you could probably construct a PDE to give that same speed up, and then it becomes the same problem.
So, is there any change? I mean, if you use another linearization instead of Kalman linearization, is it expected that it behaves for the same regimes of R? I mean, this speed up if R is larger than 1. Is it also true for another linearization, or that could change?
I think it would roughly be the same. So there is another paper with a totally different linearization technique, which I don't know very well, or at all really. It's this homotopy method where you take, you slowly move the trajectory to a linear one. But I don't know how they do it. It's some differential geometry techniques, I think. But the R that they get is where they prove that it works for less than, so here it's R is 1, less than 1. The R that they showed is actually more like 1/4. So they had actually even a tighter bound where they could show for sure the error is bounded. But this R is such a loose bound in the sense that, as you can see, like this, in this case, we have R is like 40,000 and it works. So that's why there's still an open question about how to better characterize the PDEs which would and would not work. Because, okay, R less than 1 definitely works, but there's clearly a class of equations which would have R much greater and still.
is that, also discretization plays a role, in the sense that if you have a different discretization of the same equation, you obtain a different F1, F2, F3. Then, so of course, if there is one discretization that produces the result of the condition that you want in order to prove exponentially, even if another you don't have this, then we could explain why some equations are solved also, some equations as an R larger than the limit.
Right.
Maybe there is another discretization that produces.
Yeah, it's true that, yeah, in general, the R is dependent on your discretization, so like the grid spacing, things like this. So, yeah, that would be definitely an approach for determining, I mean, how far can you push R? I mean, I mean, I'm not even sure if discretization, I mean, discretization should always, it shouldn't change whether there's exponential or quantum functional or not. So that's, but I'm not even sure if that's like a tight thing to conjecture. So I think it's true, but I don't know actually even if that's true.
No, what I mean is that this can be used if there is a way in order to prove the things for a general discretization with specifying that.
Yeah.
Then maybe you can actually discard the larger R's that you can solve efficiently.
Right.
Because this is just a product of the discretization.
Right. It would just be showing that really that discretization can't break it as well. But yeah, I think that's yeah, that sounds like a good approach.
I have a question related to the proof that uses state discrimination to show that there cannot be a quantum advantage.
Yeah.
So, okay, if I understood the proof correctly, you mean that if you initialize the system, it has two states that are very near, they have a large overlap, but your chaotic equation separates those two very near states, then you could use the simulation of the chaotic process to make state discrimination.
Yeah. I mean, the idea is that the black box only prepares one of them. It's just that you know the two options.
Mm-hmm.
And then you evolve that one state it prepares,
Mm-hmm.
just evolve it in time,
Mm-hmm.
and then use that state later.
Okay.
But there's different ways of thinking about evolving in time, where one is that it requires lots of copies of that initial state,
Mm-hmm.
and that's the normal way of thinking about it. So when I say queries,
Mm-hmm.
you can replace it with copies.
Okay, and you always assume that you are acting on these copies in a separate way, so you cannot use two copies at a time to build an algorithm.
Well, to do the nonlinear dynamics, you'd need lots of copies of the states.
But you use each of them in separately, or not?
Well, the linear systems equation would require like a
minimum
huge
for the-
register,
yeah, okay.
which would be basically lots of copies
Okay, yeah.
in a row.
Okay, thank you.
Any other question? We'll start too late, so people will
Yeah.
have me.
I'm also here for this week and next week.
Okay. So we have
No more questions? Thank you.